Okay, now we're going back to Google Colab on Jupyter Notebook that we have created outside of those validation exercises, a beam exercise. So here again, the beam is 9 meters long. It has a section of IPE 330, and it's subjected to a 10 kilonewton per meter gravity load, then to a 30-minute standard fire, where we assume a typical thermal gradient or fire loading of the beam. We observe three things: the midspan vertical deflection, the axial load in the beam, as well as the midspan moment in the beam. So let's start by doing this boundary condition parametric study. So first of all, we do pip install of OpenSees Pi and the visualization module. And we import those along with NumPy and CSV. This is for storage of information so we can compare those three different parametric study results in one plot. So just calling up a CSV or Excel. Then next, we're wiping the entire model, creating the model space. This time, we don't have one node as in the previous validation study. We have 11 nodes or 10 elements. So we have to create a for loop for that. And so we create an element, this time a beam with 10 elements. And we're fixing the first node and the 11th node. First, we're going to do a pin roller study. So you can see that translational degrees of freedom are fixed on the first node. The rotational is free. And on the second node 11, this time, the axial, translational degree of freedom in the X direction is free. In the Y direction or the vertical direction is fixed, and rotational degree of freedom is fixed because this is a pin beam. So we define a boundary condition, and we define a material property which is identical to what we have previously done. We define the cross section. This is also identical what we have done, and you can see the cross section over here. And then you define your element with 5 beam integration points. And now you're running the analysis, first applying the gravity load. So UDL is the uniform distributed load. You can see this is in terms of Newton units. So it's 10,000, that's 10 kilonewton per meter Newton. The element load will be beam uniform, and we're just going to apply that load. And here, don't forget to put the negative sign here because we're applying in the negative direction of the vertical Y axis. And we do have 0.1 increments up to step 1. So we will, incrementally apply this load up to 10 steps. Let's do that and store that information. So we have stored the information here, deflection, axial load, and moment information. And now we're gonna keep the gravity load constant. This is where it is for. And then we're gonna increase the temperature in the beam incrementally up to 825 degrees on the top flange and 690 degrees, 825 degrees on the bottom flange and 690 degrees on the top flange incrementally. And how many increments do we have? This time we're going to do it much slowly because this is a very nonlinear problem. So we're going to start with only 1% of the increment, and we're going to do 100 increments in total. And this is going to run a tiny bit longer. And we're going to store all that information, meaning the deflection at the midspan, the axial load, as well as the moment at midspan. All right, it did run. All right. Now we're gonna store this data and make sure that you are defining number one. So step number one, D1, P1, and M1 as these parameters. We're gonna store it into CSV. And now we're gonna go back and change the boundary conditions. Now I'm gonna do a pin beam. So I'm only changing this over here, but I have to start from the beginning. So I wipe it. I put the boundary conditions, material definitions, cross section, element properties, loading, and the fire loading. Done. Now what I'm gonna do is I'm gonna store this data, but I need to make sure that I don't overwrite the same parameters. So I'm gonna change it to step 2, M2, and then also make sure that I am reading those correctly. All right, I run it. Now I go back and I change the boundary conditions again. This time I make it fix. So I'm fixing the rotational degrees of freedom. Again, I'll go from the beginning, wiping the model. Applying the load and the fire load. And this is going to be my last run. And then you'll see that we will get these plots compared to each other as we have seen in the assignment background module. All right. Now I'm going to change my last set of parameters to number 3. Run this analysis. Now it has stored all that 3 data. Now I can go ahead and run this only once just to compare these 3 outputs for these 3 boundary conditions altogether. So here is the midspan displacement. You can see the pin roller, pin, and fix behavior up to 30 minutes. And next will be the axial load. And the last one would be the midspan moment. The definitions and explanations of how these behaviors are compared are already in the assignment background lecture. So please go back to that lecture to try to understand why we get these different behavior of the beam with different boundary conditions subjected to the same fire and gravity load. So next, we're going to switch to changing not the boundary condition this time. So we're going to keep it a pin beam, but we're going to apply a different load. So the utilization ratio, the gravity load of the beam will be different. So let's install the OpenSees Pi first, and then import the data. I'm going to start fresh, but everything is going to remain the same here. You can see that we are talking about a pin beam. So this is just make a comparison between 2 loadings. So we'll start with the pin beam. Do the same exact analysis as we have done before. So again, here we're applying to 10 kilonewton meter per meter uniform distributed load. So we're not changing anything. So pretty much we are running the same model, and there's a purpose to that. So we would like to store that model. into a different set of parameters. So we run the fire analysis as before. And what we're going to do here, we're going to change this to step 1, D1, P1, and M1. When the running is complete, all right. Now we're gonna save it to a file. Now we're gonna go back, and change the loading to only 100 newtons instead of 10,000 newtons or 10 kilonewtons per meter. We are changing it to 0.1 kilonewtons per meter. So we are decreasing the load initially, and observe if there's any changes in the behavior of that beam. So we wipe it clean. It's still a pin-pin beam, so we're not changing the boundary condition. We are just changing the load, initially load. And the fire also does not change. It's the same fire, 30-minute standard fire. We wait until the run is complete. And this time we're gonna store it to another set of parameters. There are many other ways to do this, but I wanted to show this explicitly so you can, when you're doing parametric studies like this, at least you have a module that you can create like this to store the information, and you can run 10 different analyses and store the information, and then put it on an Excel and compare it somewhere else. You don't have to do it on Jupyter Notebook. You can do it, graphically show it on Excel. Or as long as you have the stored data, you can plot it any way you like. So what we're gonna do is, second run. So this is stored. Now those are the two things that we wanted to compare. So we're gonna go to the end of the module where we basically plot these two different spots. So probably I need to change that to step 1 and step 2. Just to make sure. All right, there we go. So you can see with high and low utilization in the beginning, the mid-span deflection will be somewhat different, but in the end, they do converge to quite similar deflection. But axial load will be significantly different. With low utilization, you will get actually higher axial load, which is expected. And of course, the mid-span moment will also be different. It will start differently, but it will converge. The shape will be quite similar, and the trend will be quite similar for both analysis, but it will obviously be different in the beginning, almost close to 0 for a very low utilization, very low gravity load, and 10 kilonewton per kilonewton meter mid-span moment initially for our base scenario, which is 10 kilonewton per meter uniform distributed load. So this is pretty much it for these two exercises. Again, just to recap, we have done a validation exercise on Jupyter Notebook on thermal expansion. We have done another validation exercise on material degradation of steel with high temperatures. We have done exercise 1, which is a beam with several elements with different boundary conditions. So it's a boundary condition parametric study. And we have done another study of the same beam, this time a pin-pin beam only, subjected to a low and a very high utilization ratio, meaning a very low and high gravity load. And we observed the same outputs, namely mid-span vertical deflection, axial load, and mid-span moment. Thank you very much for listening.